The photograph captures the exact moment a warship ceases to be a weapon and becomes a bonfire. It is one of the most reproduced images of the 20th century. A massive column of orange flame and black debris erupts from the forward section of a destroyer, dwarfing the tugboat beside it and the dry dock beneath it. To the casual observer, this is a death portrait. It looks like the end of the line. But in naval salvage, a photograph is not a diagnosis. The subject of the image is the USS Shaw, a Mahan-class destroyer sitting high and dry in Floating Drydock No. 2. The date is December 7th, 1941. The ship has just suffered a catastrophic magazine detonation. By all conventional logic, she is dead. But the physics of the explosion are more precise and more strange than the fireball suggests. To understand why the Shaw exploded, one must understand the geometry of the trap. A destroyer in open water is a hard target, capable of maneuvering at high speed and using the ocean as a heat sink. A destroyer in a floating dry dock is a stationary victim. Floating dry dock. Number 2 was essentially a massive steel bathtub with hollow walls. To lift a ship, the dock operators pump water out of the walls, raising the floor until the vessel's keel rests on heavy wooden blocks. The water drains away, leaving the hull exposed to the air for maintenance. This creates two critical vulnerabilities. First, the ship is immobilized by gravity. It rests on a specific arrangement of blocks, and if the dock lists or twists, the ship can slide off and crush its own hull plates. Second, the ocean water that normally cools the hull and provides firefighting suction is gone. On the morning of the attack, the Shaw was sitting on these blocks, completely exposed, alongside the yard tug Sotoyomo. Sometime between 0755 and 0915, the second wave of Japanese dive bombers reached Pearl Harbor. The USS Shaw was hit by multiple bombs in quick succession. Reports indicate the weapons were likely 250-kilogram general-purpose bombs. The strikes smashed into the forward gun platform area and the bridge wing. They did not punch deep into the ship's vitals, but they did something worse. They ruptured the forward fuel oil tanks. Liquid fuel poured out of the breached hull and pooled on the dry dock floor. In the open ocean, burning oil floats away on the current. In a dry dock, there is nowhere for the fire to go. The Shaw was suddenly sitting in a burning lake of her own fuel. The flames licked up the steel sides of the hull, turning the plating into a conductor. Inside the ship, the temperature began to climb. The dry dock crew and the ship's force attempted a desperate countermeasure. They deliberately flooded the dock, trying to smother the burning oil and bring the hull back under cooling water. It was the correct decision. But the damage was already done. The flames had already baked the forward section, and the heat continued to drive inward even as the dock went down. The heat transfer continued. Deep inside the forward hull, the 5-inch powder magazines were baking. Shortly after 0930, after roughly 20 minutes of relentless fire and heating, the forward magazines blew up. The pressure tore through the ship's structure, hurled the bridge superstructure into the air, and severed the bow at about frame 65, leaving only fragments of bottom structure still clinging to what was left. The forward third of the ship collapsed into the water. The floating dry dock, now flooding uncontrollably, sank to the harbor bottom. The USS Shaw was left in a chaotic state. Her bow was a tangled wreck lying on the submerged dock floor. Her stern was still buoyant, floating weirdly above the sunken cradle. And somewhere in that same wreck-strewn dock space, the yard tug Sotoyomo had gone down as well, caught in the debris field. This created a nightmare scenario for the salvage teams. They were not just dealing with a damaged ship. They were facing a puzzle involving multiple wrecks tangled together in a grid of submerged steel. The dry dock had to be cleared and repaired, but that work could not move forward until the destroyer's wreckage was freed. It meant dangerous, exhausting underwater labor in filthy, oil-dark water, patching damage, clearing obstructions, and stabilizing wreckage under constant risk. The Shaw had lost her bow, she had lost her bridge, she was on fire and entangled with a sunken tug. But the explosion had missed the aft engineering spaces. The turbines were cold but intact. The decision was made before the smoke cleared. The Shaw would not be scrapped. She would be resurrected. But first, the engineers had to figure out how to separate the living ship from the dead metal. The most dangerous weapon deployed against the USS Shaw was not the high explosive carried by the Japanese aircraft. It was the fundamental law of thermal conductivity. When the bomb struck the forward section, the immediate violence was kinetic. Steel tore and fuel tanks ruptured. But the kinetic phase ended quickly. The bombers departed. For those 20 minutes, she sat in the dry dock, wounded, still standing. To the men fighting the fires, it felt like the danger was ebbing. They were wrong. A silent, invisible process was already underway. Heat soak. Steel doesn't just burn, it conducts. With the hull sitting beside a basin of flaming fuel, the plating became a thermal bridge, carrying energy inward through bulkheads that were never meant to be insulation. The fire didn't have to reach the ammunition to destroy the ship. It only had to cook the steel that separated it from the forward 5-inch magazines, packed with tons of nitrocellulose-based propellant. Inside those compartments, the heat had nowhere to escape. It built, radiated, and drove powder and fittings past their limits. When the magazines finally let go, the change was instantaneous. Pressure hammered outward, decks and bulkheads failed, and the ship tore open at frame 65. In a moment, the bow ceased to be a ship's front end and became wreckage. The tragic reality of this chain reaction is measured in lives. 24 men were killed, many of whom had survived the initial air attack but were caught in the blast when the forward magazines went up. They were victims of the delay, the gap between the bomb hits and the explosion that drew people forward just as conditions crossed the point of no return. When the smoke finally cleared, the wreckage drew an almost surgical line. The bow was not just damaged, it was practically erased, twisted plating and fragments lying submerged on the bottom of the dry dock. But after frame 65, the heat had failed to carry far enough. The machinery spaces were cool, the turbines were untouched. The attack had finished what it could do. What came next was salvage. The salvage operation for the USS Shaw began with a wreck-strewn layout that would have stumped a naval architect. In the mud of Pearl Harbor, 3 distinct vessels were jammed together. At the bottom was Floating Drydock No. 2. On its block sat the Shaw, what was left of her, and somewhere in that crushed, submerged space lay the yard tug Tsutoyomo. The salvage engineers faced a specific type of geometry trap. The dry dock had to be made serviceable again, but raising and stabilizing it was complicated by the wreckage and the loads trapped inside. A situation that demanded slow, methodical clearing before any major lift could safely proceed. They could not tow the Shaw out because her severed bow was a mangled mass of steel acting like a heavy anchor, pinning the ship to the floor. The solution was brutal but necessary. They had to finish what the explosion had started. They had to finish what the blast had started. Cut the stern free and leave the bow behind on the floor. This required careful cutting and clearing work by trained salvage personnel. Twisted structure had to be opened, connections severed, and hazards controlled, so the surviving hull could be freed without causing new flooding or structural damage. It was slow, dangerous labor, the kind that turns a wreck into something that can be moved again. While the cutters worked on the shell plating, the engineering team went below decks in the stern section. What mattered was not the appearance of the wreck, but what the bulkheads had saved. The after-fire room's watertight integrity had been compromised only slightly, 10 to 15 inches of water sloshing across the deck plates. The boilers were undamaged. The plant was cold, but it was there. Once the final cuts were made at frame 65, the cut line, the Shaw was no longer a ship in the usual sense. She was a floating stern section, a truncated vessel ending abruptly in a jagged wall of steel. The dock crew carefully manipulated the buoyancy. The Shaw's stern lifted off the blocks. The dead bow remained on the dry dock floor, a heavy pile of scrap destined for the torch. The extraction was a delicate maneuver. Tugs hooked onto the stern and gently pulled. There was a grinding of metal on metal, and then the hull slid free. The surviving section of the USS Shaw drifted out into the harbor channel. She was ugly, unbalanced, and open to the elements, but she was afloat. The salvage team had won the immediate battle. They had saved the propulsion plant and the hull. Now they faced a new impossibility. This half-ship, with no bow and no bridge, had to be prepared for a voyage that no destroyer was ever designed to make. The survival of the USS Shaw now hinged on a calculation that balanced risk against time. The standard procedure for moving a non-seaworthy hulk across an ocean is a tow. A fleet tug hooks a cable to the wreck and drags it at 5 or 6 knots. It is slow, safe, and tedious. But in early 1942, The United States Navy did not have the luxury of time. The Pacific Fleet had been decimated. Every hull was needed on the line. The commanders made a decision that defied the optics of the situation. The Shaw would not be towed to California. She would steam there under her own power. This presented a significant engineering challenge. A destroyer cut off at frame 65 is essentially a steel bucket trying to push the ocean. Without a bow to part the water, the flat transverse bulkhead would act as a massive hydrodynamic brake. The resistance would be immense, and the structural stress on the remaining keel would be catastrophic. The solution was to build a prosthetic nose. In the dry docks of Pearl Harbor, welders fabricated a temporary false bow. This was not a graceful structure. It was a short, blunt fairing made of light steel plates, designed solely to streamline the water flow around the jagged severance point. When the installation was complete, the Shaw presented one of the most bizarre silhouettes in naval history. The false bow ended immediately forward of the bridge and the smokestack. The ship looked like a sawed-off shotgun. Some sailors joked that she looked stubby, ridiculous, top-heavy, and truncated, a floating caricature of a warship. But the ocean does not care about aesthetics, it cares about fluid dynamics. The false bow served a critical purpose. It converted the flat drag of the bulkhead into a hydrodynamic wedge. This allowed the hull to slice through the waves rather than smashing into them. It restored the longitudinal strength of the ship, ensuring that the keel girder would not snap in the heavy swells of the open Pacific. In early February 1942, the Shaw cast off her lines. She turned her snub nose toward the open sea and throttled up. The journey to the Mare Island Navy Yard was 2,400 miles of deep ocean. The crew watched the temporary welds anxiously. If the false bow failed, the Pacific would hammer the open bulkhead, potentially flooding the ship instantly. The performance of the cripple stunned the fleet. The Shaw did not limp. She ran. The engineering plant, the same turbines that had survived the magazine explosion, pushed the truncated hull through the water with unexpected power. She made the voyage under her own power, escorted and watched closely, proving that the temporary false bow had done its job. It reduced the brutal drag of the open bulkhead and carried the loads around the hull instead of into it. For days, the Stubby steamed east, a strange mechanical chimera crossing the empty ocean. She was a testament to the resilience of the Mahan-class design. Most ships that lose a third of their length sink. The Shaw was not only floating, she was making fleet speed. When she finally passed under the Golden Gate Bridge and entered San Francisco Bay, she was greeted not as a wreck, but as a victor. She had survived the fire, the blast, the sinking dry dock, and the ocean crossing. But she was still only half a destroyer. The final phase of her resurrection required a heavy industrial intervention at Mare Island Navy Yard. In the summer of 1942, the United States Navy was fighting a war of attrition that it could not afford to lose. Every hull was a strategic asset, and the fleet was critically short of destroyers. The engineers at Mare Island chose a repair strategy built around heavy prefabrication, constructing major sections in advance so the final graft could happen fast once the ship was in the dock. This is the engineering challenge of prefabrication. In traditional shipbuilding, a vessel is built from the keel up in a linear sequence, layer by layer. Prefabrication breaks this linearity. It allows different parts of the ship to be constructed simultaneously in different locations, decoupling the construction timeline from the physical presence of the ship. Building a bow section for a ship that is not physically present requires a fanatical devotion to blueprints and tolerances. The workers were fabricating a three-dimensional structure weighing hundreds of tons. It was not just an empty steel shell. It was a complex compartment filled with piping, electrical cabling, ammunition hoists, and ventilation ducts. It had to match the dimensions of the existing ship perfectly. If the new section was too wide by half an inch, or if the deck levels were misaligned by a fraction, the graft would fail. The engineers were essentially building a massive steel puzzle piece for a puzzle that was still out at sea, far beyond the horizon. When the Shaw finally arrived at Mare Island, the surgery began immediately. She was floated into a dry dock and the water was pumped out, settling the hull onto the blocks. The first step was to remove the evidence of her survival. The temporary false bow, the blunt steel fairing that had allowed her to cross the ocean, was cut away with torches. The stubby profile that had defined her silhouette for months was discarded as scrap metal. Then came the heavy lift. The new bow section, fully formed and looking like a detached building block of a warship, was positioned in the dry dock. The alignment process was critical. Huge jacks and wedges were used to manipulate the steel block until it met the severed bulkhead at frame 65. The match was precise. Welders moved in to fuse the two sections together. They stitched the longitudinal stringers and the hull plating, restoring the structural continuity of the keel. They connected the severed pipes and spliced the electrical runs, integrating the new nervous system with the old. This was not just a cosmetic repair. The new bow restored the Shaw to about 341 feet overall. It restored her buoyancy distribution, her hydrodynamics, and her weapon systems. The transformation was total. When the dry dock was flooded, the ship that floated out was no longer a cripple or a curiosity. The visual deformity of the sawed-off shotgun look was gone. She was once again a sleek 1,500-ton Mahan-class destroyer. The operation had been a complete success. The heat had taken her bow, but it hadn't taken the ship. The explosion had failed to sink her. The ocean had failed to break her. Now, the industrial might of the shipyard had erased the scars. The USS Shaw was whole. She was reloaded with ammunition and fuel. She turned her new bow west, back toward the war that had tried to destroy her. The true measure of a naval salvage operation is not found in the dry dock records or the engineering reports. It is found in the operational logs of the fleet. When the USS Shaw steamed out of San Francisco Bay, she was no longer a victim of the Pearl Harbor attack. She was a weapon system returned to the line of battle. The Japanese Empire had claimed her destruction. The photographs of her magazine detonation had circulated around the world as proof of American defeat. But in the years that followed, the Shaw provided a definitive counter-argument. She earned 11 battle stars. This number is the ultimate validation of the decision to save her. A battle star isn't a participation mark. It signals meritorious service in active combat zones. The ship that had been severed at frame 65, burned by oil and blasted by its own ammunition, went on to fight in some of the most vicious campaigns of the Pacific War. She did not serve as a rear echelon guard ship. She was thrown into the offensive. Instead, she served across the Pacific in hard campaigns, screening larger ships, supporting landings, and enduring typhoons and air raids. For 3 years, the machinery that had once sat cold in the bottom of a sinking dry dock drove her through combat zones again and again. The stern section that had been separated from the dead bow proved that the heart of the ship had never actually stopped beating. There is a profound psychological dimension to this survival. In naval warfare, the identity of a ship is a powerful totem. When an enemy believes a ship is sunk and that ship reappears to fire its guns, it undermines their strategic confidence. The Shaw became a ghost that refused to fade. Every time she appeared on the horizon, she proved that the damage control calculations made in December 1941 were correct. The physics of the heat soak had destroyed her bow, but the logic of the salvage engineers had saved her soul. That photograph is still the world's shorthand for the Shaw, one frame of catastrophe. But it isn't the whole arc. The photograph captures a moment of failure, but the ship herself represents the triumph of engineering resilience. The Shaw demonstrated that a warship is more than the sum of her steel plates. As long as the keel can be made continuous, and as long as the turbines can turn, the ship is alive. The wreckage of her original bow remained in Hawaii, scrapped and melted down to build new weapons. But the Shaw herself survived until the end of the war. She even survived the peace. She was decommissioned in 1945 and later sold for scrap in 1946. Not as a casualty of war, but as a veteran who had finished her watch. In the end, the salvage of the Shaw was not just about restoring 1,500 tons of displacement to the Navy list. It was about refusing to accept the verdict of the bomb. It was a statement that in the United States Navy, even a ship that has been blown in half is not finished until the engineers say it is finished.